So, without further ado, here's the father of the Roy language, Brian McKenna. Pow!
Thank you. So, who am I? I am a Scala developer. Does anybody here develop any Scala? Wow, that is amazing. That is a huge number of people. So, I work for a company called Precog, where we make we're working on a big data query language and data storage system. So, we're using Scala, and we're doing it in a purely functional way. So, I love purely functional programming. Not half functional programming, I'm full on. And I think this is like the only way that we've been able to actually make a large system. I don't think that we could have done this in a sane manner with any other, like with an OO system or anything like that. We had to use purely functional programming. So I've been doing purely functional programming for I guess about 4 years. But before that, I was one of these. I've been doing JavaScript for about 10 years. That was like my first language, my first real language. That's what I keep coming back to. I mean, I do a lot of web development. I have to use JavaScript. Even though I like functional languages, I come back to JavaScript because I have to make web pages. I have to make client-side applications. So that's kind of my motivation into JavaScript and functional programming. So I've been working on this library recently called Bacon.js. There's a hidden message in there if you can see it. So Bacon.js is some horrible library that I made that allows you to do operator overloading, as well as it's got functional data structures and ad hoc polymorphism, all the good things, and it's completely immutable. But I feel like I'm really pushing JavaScript to its limits, like operator overloading in JavaScript. Did anybody know that was possible? I didn't. It took me forever to figure that out. So this is a monad syntax inside of JavaScript. It actually works, which is amazing. So I've got these stuff. I've got proto-based testing for like quick check and Scala check from the functional community. Operator syntax for like doing monad comprehensions. Functional data structures and immutability everywhere. So that's all good, but it's not good enough. It's really hard to write JavaScript programs that do what I wanted to do. They do the wrong things. I write some really trivial JavaScript like you saw this morning in the hands-on session. If anybody was there, I was writing really simple JavaScript and I still got it wrong. That doesn't happen so much in Haskell for me. So I've been working on this language called Roy. This is the logo. It's an Australian sheepdog. I'm Australian, sorry. So Roy is an alt.js language, or alt.js language. Has anybody seen CoffeeScript before? A couple people seen CoffeeScript, yeah. So it's similar to that. It's a language that compiles into JavaScript, and it's meant to compile into readable JavaScript. There's actually I maintain a list called I maintain a list of these languages on altjs.org. There's so many, it's crazy. So I had to create my own, of course. So Roy is different in that it has types. Not many of these alt.js languages actually have types or any type safety. Type safety is really, really important because, I'll quote Simon Peyton-Jones, types are the world's most used formal method. It's Simon Peyton-Jones, so he makes up a number. 6 orders of magnitude. So if you think about that, we're actually proving things. We're using a formal method to prove things when we write with types. I think that's pretty amazing. We're actually proving parts of our code are correct. And it's also functional. There's a couple of typed languages, like TypeScript, but they're not actually functional. They don't help you with immutability. There's still an OO language with some types added on. So this is the second part of Roy. It's a functional language, and what I mean by that is that it's completely immutable. So if you stay within Roy, you can't mutate things. So I like to think of it as a cross between CoffeeScript and something like a Camel or Haskell, which is what I'm familiar with. So this is our first line of Roy code. Can anybody guess what this does? It's pretty complicated. Let's see what it compiles into. So that's the JavaScript compiles into. That's pretty readable. It doesn't compile into 1 megabyte like Dart used to compile into. 1 megabyte of JavaScript just for a hello world. This compiles into a couple bytes, which is awesome. So this is our second line of Roy. Can anybody guess what this compiles into? I'll show you. That. So it's really, really, really simple translation. It's a really simple compilation step. So here's some problems that I have with JavaScript. Weak typing, duck typing, monkey patching, callback hell, which is Node.js, and modules. So let's solve the first problem of weak typing in Roy. So this won't compile. How good is that? Something that doesn't compile. Yeah. So a string of hello adding 2, it doesn't make sense. So the compiler should catch that and say, hang on, this expression doesn't make sense. I'm not going to give you a program for that because you're nonsense, really. So that's a good thing. We're not compiling untyped safe programs. We're not compiling programs that are going to be buggy. So here we've got a function. So it's called f. It takes an x and returns back a number. And it returns back x. So what does that mean x is? X is a number. So we can just use that function. If we try and pass it a string, so we pass in, down the bottom we've got a string of 100. It doesn't compile. It says, I expected a number, but you gave me a string. And that's the JavaScript compiles into. Really, really simple. So the second problem I have with JavaScript is duck typing. Whoa, what the? Whoa, that's amazing. Too fast for you. Wow. I wrote this presentation software, so there you go. And it's not purely functional, that's the problem. So duck typing is a feature, right? We've got a duck here. Good looking duck. So here we've got a function. It takes an A, and it returns back a string. So we've got a.name and a.sound. Now look at the bottom example we've got. So we're passing in a tree. A tree doesn't have a sound. So our code is going to return back tree sounds like undefined. That doesn't make sense. So let's use structural types. It's a form of statically typing, duck typing. So now our bottom code example won't compile. So this is all Roy code now. Up the top, we're doing the a.name and a.sound, and we'll concatenate a string together. Roy is able to look at that and say, oh, you need to concatenate all these things together, and it's an object, and it looks up the properties, and it figures out exactly what you need. So this function is actually typed as a function from an A with a name of string and an A with a sound of string to a string. So static duck typing, how cool is that? Sum types is the other form of duck typing. So we've got product types, which is a structural type. So you're adding things together, and then you've got sum types, which is a form of disjunction. So we're saying here this is an option of A, and A is a type. So we can have a sum of some sort of type, or we can have nothing. So this is representing null at the type level. So we have to handle this. We can't just say this is an A, because it's an option of an A. I'll show an example. This is the JavaScript compiles into. Just a function constructor. We're doing not this instance of sum, so we can just use it as a function. We don't have to worry about if it's a constructor or a function. It's just a function. We can just call it. So now that we've got this option type, we can pattern match on it, and we have to handle the nothing case. We can't just pretend like, oh, it's null, we'll let it crash at runtime or whatever. We have to handle it. So we have to do pattern match, or we have to use some sort of combinator that does this pattern match. So here's non-zero. It takes in an O. That O is either a sum of S or a none. In the none case, we return back a number, so this function has to return back a number. If it's sum of s, then it returns back that s. So that means that this takes in an option of a number and returns back a number. So we're kind of unwrapping it, but we've got a default value of 0. And this is JavaScript that compiles into. It does an if statement to do a instance of check. So it checks if it's a sum, or it checks if it's a none, and returns back the values. Extracting it out in the meantime. So now we can use it like that. So we pass in none, we get back 0. We pass in a value of, we pass in a wrapped value of sum of 1, and we get back 1. So it unwraps it for us. And that's the JavaScript compiles into. Simple. So monkey patching. I actually gave a talk similar to this at another conference, and somebody said, monkey patching is a feature, don't take it away from me. I don't want to take it away, I just want to make it safe, okay? This is unsafe stuff. This is monkey patching in action. So in ES6, there's a contains function on strings. So you can go string, does it contain this thing? ES6 defines this index property as well, so you can say, do you contain this string from this index onward? And here's mutools. I don't know if you can see that, but mutools defines a contains function as well. But it doesn't take an index, it takes a separator. So it splits up a string and then checks if that thing is in that array that it's split up into. So what's the output of this function then? It depends on if we've included an ES6 shim after mutools, or if mutools is, because we're overriding the global prototype of string, it matters in what order we define things. And because it's a global, you've got other functions that depend on it, and things break. So this is actually taken from an issue in the mutools bug report. So it's actually an issue on their tracker. So let's try and do this a little bit safe. Here's how we do it with type classes. So Royce supports a form of ad hoc polymorphism called type classes, which means that we can define some sort of abstract function, and then we can give a concrete implementation that is looked up by types. So we've got this type class called with contains. It has a contains function, so it's a function that takes a string and then another string, and then some sort of a, and returns back a boolean. So in ES6, we can just use index of, because that's exactly what the index of function does. It takes in a number as the third parameter. Or we can do separated contains, which takes in a string as the third parameter. And when we've got these two lines down at the bottom, so one is a string and one is a number. So it actually dispatches based on the type. So the bottom one, we have a string. So it looks up the separated contains, and then does that code. If we've got a number, it looks up the index contains. So we're dispatching based on types, different implementation based on types. And this is JavaScript compiles into it, just hard codes the dictionary lookup. So index contains or separated contains based on the type of the input. So that was safe ad hoc polymorphism or safe monkey patching. So the fourth problem is very common in Node.js programs, but we're gonna solve this using monads. Yeah, monads. Did I hear that? No, okay. So what's callback hell? This is callback hell. Has anybody written any Node.js before? You know this stuff. This is Node.js. So let's see what this code does. Okay, so if we get a request for the index page, then we go and look up the user from using the parameter. Then we go through the user and look up a user. Then we go through the database. We look up that user by the username, and then if there's an error, then we return the error. Then we get the cursor. Then we go loop through the cursor. And if there's an error, then we return that error. And then we send a response. Like that is so tedious to read. It's a pyramid of logic mixed with error handling logic mixed with actual business logic. Wouldn't it be good if we could make this look like clean code? So we define this thing called a, has anybody used the jQuery deferred function before? A couple people. So jQuery deferred is a way of, handling asynchronous callbacks inside of jQuery. So jQuery, when you do an AJAX call, it returns back a deferred. So I'm actually using jQuery's deferred here to define a monad that can actually solve the problem that we had before. So here we're defining, if we get a return is just something that will take some sort of value and wrap that up in a deferred. So that's what that return function is doing. It creates a new deferred, puts that x in there, and then returns that back as a promise. And now bind is a way of sequencing deferreds. So we've got a deferred, then we want to take the value from the deferred and pass it to a function that returns a deferred. So we're sequencing up a heap of functions that return deferreds. So that's the jQuery pipe function. Does it for us. And that's JavaScript compiles into a normal, it's a normal object with function calls in it. And this is what we can write now. So this is synchronous looking code, but it's actually completely asynchronous. So we're doing an AJAX request, getting the value out, doing another AJAX request, getting the value out, and then we're adding those two and returning that back as a promise, or as a deferred. So we've got two deferreds, we've extracted values out and made a new deferred. So we've got a single deferred from two deferreds. And that compiles into that. So it actually compiles back into Backhaul, into Node.js looking code. But all we had to do is write synchronous looking code like that. So you can see that it does an AJAX call and then does a bind, which extracts out that value and then continues on. And all that is asynchronous. And the fifth problem I have are modules. Basically, there's three main ways at the moment of defining JavaScript modules. The next version of JavaScript is going to have modules built in. But at the moment, we have to deal with this. So browser globals is where we have window.jQuery equals jQuery, and then you just use jQuery. You don't have to include anything. You just include the script, and it's there. It's set on the global object. Common.js is in Node.js, so you do a x equals require x, and you get the x imported. Or there's AMD, which is actually it actually works pretty well for browsers because it's an asynchronous module definition, where browsers don't want to block, so they want everything asynchronous. So all of these work better in different situations. So I decided that I'll compile to all the module standards. Why only support one of them? We need different module standards. Well, we need different module loaders for different types of applications. So we write this module in Roy once. This is one module that we write. So this is a module that just shows that we're importing settings, and then we export something called app name, which uses the settings module. Just a really simple example. If we export that to, if we compile that to a browser module, it'll compile into something like that, where it just expects settings to be assigned on the global object, and then sets its exports on the global object. So they're all just setting things on the global object, and it's not extremely nice, but if you need to compile something simple if you need to compile a simple Roy module to a browser, then that's what you do. If you compile it to Common.js, then it creates a Node.js module where it just sets it just does a require to get the settings module, and then it does an export to export its identifiers. And with AMD, it defines its dependencies, and then exports what it needs to export. So that's how Roy solves some of these problems. So Roy is trying really hard to be safe. So it adds static typing to weak typing and duck typing. It uses a safe form of ad hoc polymorphism, so it doesn't go overriding things. It uses immutable type classes to solve monkey patching, to get the same effect as monkey patching. It actually does a lot more than monkey patching, if you want to read into that. And it solves callback hell by using monads and monad syntax. So you write synchronous-looking code, and you get compiled into callback hell that you can use in Node.js, which is still completely asynchronous, but looks synchronous. And I'm trying to solve modules, so compiled to all the different module standards, you just write your module once. You don't have to worry about it. So in the future, I'm going to be working on functional lenses. So this is going to make immutability easier than Haskell, which I think is pretty amazing. Haskell doesn't have these functional lenses built in yet. They've been talking about it for a long time, but it's not built in. And if you think about it, like Haskell programs are completely immutable. So if Roy's beating it, then I'm pretty happy. So here's an object. This is me. I've got an address, and I've got a number on my address, and I've got a street on my address. Now, it's really annoying when you're writing immutable programs to go and update this. So in a JavaScript program, you probably do me.address.number equals 50 or something, and you've updated it. But you've updated every reference to it everywhere. So anything that wants to read that object again gets back number 50. Now, in an immutable program, what you'd have to do is copy the object, and then set the address, and copy the address, and then change the number inside of it. So you've got this nested update that you have to manually do. Now, lenses solve this problem where we can create a person street lens here. So we've got compose, street, and address. So this is going to create a lens all the way through to the person's street. So if I do a get, I get back that value from the street on that person. If I do a set or do an immutable copy of that nested data structure and give it back. So if I do set person street of Walnut Street and give it my object, then it'll give back that my object with just the street updated. And it hasn't updated it for every reference to it. Like there could be other programs referencing it, and they get the old data. That's fine. It's just inside of this function or inside of whatever scope I'm in, I'll have that updated address, which is pretty cool. And I'm going to copy Haskell's new feature that came out within the last month. So they've added this flag called Deferred type errors. And the idea is that you can write code like this. So to a Haskell programmer like me, this code doesn't have a defined output. This is wrong code. To a JavaScript programmer, this will always print 2. It does print 2, right? I mean, if true, then print 2. It prints 2. JavaScript, a Haskell program will look at that and say, oh, to do +1, what are you talking about? That doesn't make sense. So with this deferred type error flag, we can actually compile this into JavaScript that looks like that, where it'll actually return, it'll actually throw an error instead of given a static type error before giving a program. So the benefit of this, like this isn't perverting static type systems or anything. The reason we want to do this is if we want to run our test, for example, we've been writing some things. We haven't been able to get it to type check. We haven't been able to give a complete implementation. But we've gotten part of the way. We want to see if some of the tests pass. Not all of them might pass, but we want to see if a couple of the tests pass. So we compile with this flag, and we get this JavaScript that will actually never print the error, so all our tests will pass for this code. But it's bringing a little bit of dynamic typing to a static type system, which is pretty cool. So you want to ship code with this flag turned on. Well, I hope not, because the static type is actually telling you you've got a bug. You've written nonsensical code. So you can actually play around with Roy. On my website, I've got roy.brianmckenna.org. It gives you a little thing like this. I'll show you how it works. So we go to roy.brianmckenna.org. We get given a couple of different example codes. So let's go look at the deferred monad. There we go. And that it automatically compiles it for us, and we can run it. And there we go, get the output. So it's really easy to play with. You can start with an example like the types, put in a type error, and it'll actually give you the error down the bottom. So that's pretty cool. So thanks, that's Roy.